Hi, welcome back. We're going to continue on with our review of some elementary vector operations, and in this video we're going to look at vector multiplication and projection. So let's start. With vector multiplication, there are two ways of multiplying vectors, it turns out. And so we're going to use each way, and the first is what's called the dot product. And sometimes this method of multiplying vectors is called the scalar product. So those two things mean the same thing. The scalar product might be more insightful, but the dot product is more clear based on the notation, as you'll see. So regarding the insightfulness of scalar product, the reason it's called scalar product is because when you take the two vectors and you multiply them together, you get a scalar as a result. Remember, we're always going to be concentrating on, am I looking at a scalar or am I looking at a vector? You've got to keep that clear. So one way of doing that is to realize that, yeah, the dot product is called the scalar product. A scalar results in once you multiply the vectors together. So if we had two vectors, let's say A and B, and we wanted to compute their dot product, we would write that like this. So we use the dot operator, so that's why it's called the dot product. And we read this, read it out loud, A dot or dotted with B. Okay? Now, geometrically, it's defined as the multiplication of each vector magnitude times the cosine of the angle between them. All right, so let me just write two vectors here. Let's say here's vector A, and maybe this is the origin. So vector A, there it is, and it has a length A. And maybe here's vector B, just a different vector. Nothing particularly interesting about these two vectors that I chose, just two vectors, right? And vector B has a length B. And notice that there's an angle in between them, and we'll call this angle theta sub AB, like that. Okay, so the dot product is defined, again, I'll say it again and then I'll write it down this time. It's defined as the multiplication of each vector magnitude times the cosine of the angle between them. So that is the multiplication of each magnitude. So that's A times B, the length of each one, times the cosine of the angle between them. So geometrically, that is how the dot product is defined. Just a small kind of caveat or a small note, there are actually two angles that separate AB. There's this bigger one too, right? They add up to 360 degrees. So the angle in this equation is the smaller of those two. It's less than or equal to 180 degrees. And this works in this works in 2 dimensions, 3 dimensions, or higher. Okay, now mathematically, this is the geometric interpretation. Mathematically, it's defined as the sum of the products of each of the corresponding component. So now, let's, because it's easier to draw, let's say that these are two-dimensional. So I have A over here, and I have B like this. Okay, so A has a component in the x direction, AX, and a component in the y direction, AY. And B has a component in the x direction and a component in the y direction, like this. Right, so remember from the previous video, we can write A like AX times little ax plus AY times little ay, and we can write b as bx times little ax plus by times little ay. And remember that this is ax. It's a unit vector that points in the positive x direction, and this is ay, a unit vector that points in the positive y direction. Okay, so again, let's get back to the dot product. The dot product mathematically is defined as the sum of the products of each corresponding component. So this is ax times bx plus ay times by. So multiply the components together, then add them. That's what you get. So that's in 2 dimensions. In 3 dimensions, so I'll come over here. We're almost always going to be concerned with 3 dimensions in this course. So this is just ax times bx plus ay times by plus az times bz. Right? So that's mathematically how it's defined in 3 dimensions. All right, so let's kind of understand this for a little bit. Try to understand it for a little bit. So I'll ask some questions. Feel free to pause the video if you need to pause the video to think about it. So I'm going to assume you're going to do that. But anyway, what is the dot product of 2 vectors that are perpendicular? And another, we've already seen names, several names for the same thing. Orthogonal is another word for perpendicular. So what is the dot product of 2 vectors that are perpendicular? Well, if that angle is 90 degrees, then it doesn't matter what their magnitudes are. The dot product is 0. So the dot product is 0 for perpendicular vectors. That's going to be very important. Actually, let's look at these vectors ax and ay, right? Ax points in the x direction. Ay points in the y direction. So those are orthogonal. Those are perpendicular. So what is ax dotted with ay? 0. Okay, here's another question. What angle should A and B make if their dot product is to be as large as possible? So again, feel free to pause the video. What angle should they make if their dot product is to be as large as possible? Well, that would be, we would want an angle of 0 there, because cosine of 0 is, or cosine reaches its maximum at 0. So that would mean we want A and B to line up. And if they align with one another, then their dot product is the maximum. And the minimum dot product is when they are anti-aligned, when they point in opposite directions. Then cosine of 180, right, is -1, and we have the minimum dot product. So that's kind of neat. Also notice that if I take the dot product of a vector with itself, like that, and then take the square root, this would be ax times ax, right? This is the mathematical definition of the dot product. So take the component times the component plus the next component, right? The y component times the y component plus the z component times the z component. So that's the square root of ax squared plus ay squared plus az squared. So what is that? That should look familiar. That is a. That is to say that's the norm or the length of vector A. Right? So that's another way of computing the norm. Take the dot product of a vector with itself, take the square root. Now the dot product is commutative. So A dotted with B, just like usual multiplication, is B dotted with A. That works. It's distributive as well. So I'll just make a note here. This is commutative or commutative, potato, potato. And it's also distributive. So what does that mean again? Well, if I take A dotted with, or maybe I do the dot product of B with C first, and then I take A dotted with that result. Okay, that's the same Oh no, excuse me. If I add vectors b and c together and then I dot it with a, that's the same as if I were to dot a with b and then add a dot c. Now, the dot product does not enjoy the associative property. It's not associative. And I'm going to ask you, think about that. Why isn't it associative? Pause the video if you like. Think about it. So it cannot be the case that this is true. It cannot be the case. And it has to do with the idea that this gives you a scalar when you do the dot product. So in here is a scalar. So dotting a with a scalar, that doesn't even make sense. So no, we're not going to do that. That's garbage. This is garbage. Okay, that's why it's not associative. Alright, so that, remember we started this video, we said that there are two ways of multiplying vectors. That's one way, called the dot product. Now we're going to move on to the second way. So I'm going to erase this. Again, feel free to pause the video before I erase that. So here's the second way, and the second way is called the cross product. And it's not a big surprise that this is sometimes called the vector product. What do you think we get when we take the cross product of two vectors? Do we get a scalar or do we get a vector? Yeah, we get a vector as the output. So that's really the crux of this whole multiplication operation. Do we want a vector as an output, or do we want a scalar as an output? And so if we want a vector, then we're going to do the cross product. And so if I had vectors a and b, we would write this. We would write that there with the x, and we would read this as a cross b. A cross b. So now let's talk about the geometric interpretation of this. Let's say again I have vector a and vector b, like that. It turns out that the cross product is the area of the parallelogram defined by a and b, and has a direction that is normal or perpendicular to the plane containing this parallelogram. So so let's just be a little bit more clear about that. So here's vector a and here's vector b. What is this parallelogram I'm speaking of? Well, we saw it a little bit in the last video. It's this parallelogram, okay? So it turns out that when I compute A cross B, I get the area of this parallelogram. Now the mathematicians, and you may have learned this in high school geometry, tell us what the area of that parallelogram is. It's the length of A times the length of B, like we saw with the dot product, but times the sine of that angle. And so this actually is that's the area of that parallelogram. Okay, so when we compute A cross B, we get the area of the parallelogram. But you say, hey, wait a second, the area is a scalar; it's not a vector. And yes, and so the direction that you get out is perpendicular or normal to this this plane, right? This is like a sheet of paper. It's a plane, so you can imagine something that's perpendicular to the plane. And so we would say this a unit vector that's normal. So a, remember, little a always means a unit vector, and subscript n for normal. So we would tack on an. So a cross b gives us a times b times the sine of the angle in between a and b times that unit normal vector. And again, just a little note here, there are actually two angles in between vectors A and B. There's this one too. We're talking about the smaller one with this equation. So the smaller one will always be between 0 and 180 degrees. So how do we calculate such a thing? And we actually calculate it. So here's the mathematical interpretation. The mathematical interpretation is with a determinant. It's a matrix determinant. So this long vertical bar doesn't mean norm in this case. It means determinant. So I'm going to put AX up there, AY there, and AZ there. And then I put the components. So I've got A first here. So I'm going to put AX. It's got an X component. It's got a Y component. It's got a Z component. And then I've got B second. So then I'm going to list B's components here. Okay, so I'm going to actually, it's kind of weird. It's kind of goofy if you're not used to it. But I'm going to take the determinant of this matrix then, right? And so that's going to give me the cross product. So let's talk about how to find the determinant of a 3 by 3 matrix. You should know how to do this already, but I'm going to review it anyway. So we start, this is how I do it. I start here, and then I actually don't want to mess this up, but I start with the AX and I kind of cross this out. So I'm gonna ignore what's below AX, and I'm gonna ignore what's to the right of AX. So, and I'm just going to write AX. So I'm considering AX right now. And then I multiply AY with AZ. And then I subtract this multiplication, AZ with BY. And then I move on. And so I go to this next guy. And they kind of alternate by signs. So the next guy is negative something. AY. So what is that something? Well, again, so I ignore what's underneath AY and what's in the same row as AY, so I'm left with AX and AZ, so I multiply those together. And then I subtract, and I've got BX and AZ. Like that. Excuse me, this should have been BZ down here. So this should be BZ here. Sorry about that. BZ. Okay, and then I move on to AZ, so then I add, right? They alternate in signs, positive, negative, positive, something times AZ. So then again, I ignore what's in AZ's row and AZ's column, and I'm left with this guy, AX and BY, AX times BY, and minus AYBX, like that. So this silly kind of operation, you know, there's a mathematical basis for this operation, but on the surface it seems kind of silly. But that's how you compute the cross product, A cross B. All right, and it's going to turn out then you have a direction that is normal to that parallelogram. Now, since there are two unit vectors that are actually normal to this, this parallelogram, here's another one, right? We use what's called the right-hand rule to decide which of those two unit vectors we need here. And the right-hand rule works like this. This is a video, so it's hard to describe this, but I'm gonna do my best. So you take your right hand and you point your fingers in the direction of the first vector, which is A. So right now, so you should be doing this too, but I'm doing this as well. My fingers are oriented along A, and then of your right hand, and then you curl your fingers towards vector B. So I'm doing this, you should be doing this, pointing towards A, curling them towards B, and then your thumb is actually pointing in the direction that we want. So if you did that with me, your thumb should be pointing this direction, not this direction. So it's this direction that I circled that we want here. That's the right-hand rule, A cross B. And so that's a right-handed system, and we're always going to use a right-handed system. This is going to come up many times, the right-hand rule. All right, now notice if you did B cross A, so just to see if you've got it, do B cross A. So align your fingers of your right hand along B and curl them towards A. Now in order to do that, you actually have to flip your hand upside down. So now your thumb is actually pointing in the one we crossed off here. So you'll see it's pointing in the opposite direction. So right away we see that B cross A is not the same as A cross B. So we would say that the cross product operation is not commutative. Okay, it actually turns out that A cross B, there should be a not equals there. A cross B is actually equal to negative B cross A. And so we call that anti-commutative, but you don't need to worry about that. Just know that it's not commutative. It's also not associative. So let me just write that out here. That's A cross B cross C is not equal to A cross B cross C. So it's not associative. Okay, but it is distributive. Okay, and I challenge you to prove these things out. You should be able to prove these out. Oh, what am I doing here? I'm not writing the correct property. It is distributive. So if I take A cross B plus C, this is equal to A cross B plus A cross C. So how would you prove these things? Well, you go to the definition and you see, do these things work out like I'm saying they work out? So I challenge you to check those things out. Okay, we already kind of did this with the right hand rule. We showed that that was not true. But how is it that this is true, right? How is it that it does not hold associativity? How is it that it does hold distributivity? So work those out on your own. See if you can prove those. All right, now finally, we're going to talk about vector projection. So vector projection we're going to need quite a bit, and the idea goes like this. Let's say I have vector B, no particular vector there, and let's say I have vector A, no particular vector there. It's often the case in electromagnetics where I'm going to need the vector projection. I'm going to need the component of A along B, which is this thing here. I'm going to do that in blue, actually. You see, if I like projected light perpendicular to B, maybe B is a screen, right? And I'm taking this literally projection. So I'm projecting light onto a screen that's oriented along B. What shadow do I get? Okay, it's the shadow that I get is the thing in blue, right? All right, so let me define a couple things here. Let's say B has a length B and A has a length A as usual, and the angle in between them is theta AB, like that. All right, and this makes a right triangle. Okay, so what I want is this thing in blue. The vector projection would be this thing, and what we would call it, we would say A onto B, like that. A projected on B, so this is A subscript B. And also, so that's the vector projection, and also is the scalar projection, just the length of that thing, A sub B, like that. So what I can do is leverage the properties of the dot product. So remember that A dotted with B gave us the length of A times the length of B times the cosine of the angle in between them. Right? So now let's take that equation and let's divide by B. And the reason that we do that is because we can interpret the right-hand side now. Check out that right-hand side. A, which is the length of the hypotenuse, times the cosine of the angle. Okay, what is that? Well, think about trigonometry. A cosine. Cosine is adjacent over hypotenuse. So that actually gives me the length that I want, right? That gives me AB with the scalar projection. So I would take my two vectors, I would dot them together, A dot B, then divide by the length of B, and that would give me the length of the vector that I want. So that this would be the scalar projection. Okay, so this operation is a scalar because A dot B is a scalar and B is the length of vector B. So this is a scalar divided by a scalar. That gives me a scalar. Now what if I wanted the actual vector though? Well, in that case, all I have to do is take the length that I just got, right? I like that length. Then multiply it by a unit vector that points in that direction. So that's a unit vector that points in direction B. So I'll draw that in red here. Maybe that's this guy. A sub B. Remember, the lowercase a always means a unit vector. So this is a unit vector that points in direction B. Okay, now just to make some simplification, so this would be the vector projection. This was the scalar projection. This is a vector projection here. Okay, and so this would be equal to A projected onto B like that. Whereas this guy is A without the arrow projected onto B. Now notice one last thing here. This guy here, vector B divided by its own length, that is a unit vector that points in direction B. Do you remember that from the previous video? That we can get a unit vector by taking a vector dividing by its own length. So there I have AB there, and so I can write this left-hand side as A dotted with a unit vector that points in direction B. That's what I've circled there in blue. So that's that entire fraction, then times AB. That's this guy here. So here's my vector projection operation. All right, so all of this should be review. All of this should be a review to you. You should have seen this in some context previously, like in your math classes. Now, everything we've done here has been in rectangular coordinates, meaning, left, right, up, down. It turns out that some situations determine some situations based on the geometry of the situation. It might be more advantageous to use different coordinate systems, like not rectangular, but other ones like spherical or cylindrical. So what are these coordinate systems, and how do we describe them with vectors? That's coming up. And so I will see you in those next videos.